In this video, we're going to begin a discussion of some more advanced techniques for counting more complex structures. We're going to start with permutations, which ask us to consider how to rearrange objects in a sequence. So here's an example question to start us off. How many ways are there to rearrange the letters in the word math? So when we think about the number of ways to rearrange the letters in the word math, we're asking about the size of the set, where each element of the set contains these letters arranged in some sequence. So for example, math itself is one such valid arrangement, but here's also THAM, that's a valid arrangement. Here's another one. And so the question that we're asking here is, how many of those rearrangements are there? The key idea here is that we can think about the question of finding these rearrangements as the question of just filling in these blanks in order. So I ask myself, hey, how many choices do I have in order to fill in this first blank? Well, when I get to this first blank, I have all four letters in the word math available to me, and so I can pick any four of them. So for example, let's suppose that I pick the A, and that was one of my four choices. Okay, so now let's think about filling in the second blank. In order to do that, I need to pick one of the letters, but I can't pick A again. I already used that, which means that I now have three choices in here. So let's suppose, for example, that I pick the T. Then, continuing in the same vein, in order to fill in this next blank here, I have two choices. I only have the H and the M left. And so here's the H. So that was two choices. And then by the time I get to the last blank, there's just one left. So I have just one choice there. So when we think about how many ways I could have done this, I say, okay, I had four choices for the first one, three for the second, two for the third, one for the last. And I'm going to use the multiplication principle in order to actually figure out how many possibilities I had here. So there were 4 times 3 times 2 times 1 possible choices, which is equal to 24 possibilities. So let's think about this in a little bit more, with a little bit more vocabulary. So we often call this a permutation. A rearrangement is called a permutation. And formally, what I just said in words, formally, we often use this multiplicative principle in order to say, hey, the number of permutations is equal to, well, it's the number of choices for the first slot put a little parentheses here, times the number of choices for the second slot, and so on until we get to the last slot. And in our case, this was equal to 4 times 3 times 2 times 1. Now, if you are looking at this expression and thinking it looks a little bit familiar, you'd be right. So the permutation formula in its first and simplest form, it says that the number of permutations of n elements or objects is, okay, so we saw our formula here. We start at the number of elements we have and we work our way down with multiplications. So that's n times n minus 1 times n minus 2 all the way down to 2 times 1. That's also the same as the product from I equals 1 to n of I, and we defined that. That's n factorial. So the main one you need to remember is right here. The number of permutations on n objects, or equivalently, the number of ways to arrange n objects in order, is n factorial. So let's continue with our discussion of how to arrange things in order. This time, we're going to consider a related but slightly more complicated question. So suppose that I have n distinct things, and I want to pick k of them and arrange them in order. So I don't necessarily want to arrange all n of the things in order. I just want to pick k of them. So here's an example. How many ways are there to make a 5-letter sequence from the letters in the word computer? So computer has 8 letters. I don't want to rearrange all the letters in computer. I just want to pick 5 of the letters and then arrange them in order. So here's a few examples of such strings. So comp u is one such string with 5 letters. RUOPC, there's another one. And here's a third one, TUCER. So all of these are arrangements of letters in the word computer. So how could we start thinking about how to count the number of possibilities we have here? Well, one way is to go back to our blanks. Okay, so here I've laid out 8 blanks for the possible ways in which I can construct the sequence from the 8 letters of the word computer. And following our logic from last time, if I were arranging the whole set of 8 letters, I would have 8, 7, 6, 5, 4, 3, 2, 1 choices at each of these stages. And then I would multiply them all together, and I would get 8 factorial. But that's if I were multiplying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's if I were taking all 8 letters, and I'm not taking all 8 letters. I'm only taking 5. And so that means, really, these last choices don't exist for me. I'm not going to get the opportunity to fill in those last 3 blanks. Those are kind of dead to me. And so the blanks I'm going to get to fill in are the ones where I have 8 choices, then 7 choices, then 6, then 5, and 4. So let's turn this into a math formula. Here I want to count the number of ways. And we just argued, okay, this number of ways is equal to 8 times 7 times 6 times 5 times 4. Okay, now in order to turn this into something a little more compact, something that I have notation for already, I'm going to do a small math trick. I'm going to multiply by 1. And the way in which I'm going to multiply by 1 is I'm going to put 3 times 2 times 1, 3 times 2 times 1, on the numerator and denominator of a fraction. And I'm going to multiply this whole expression by that fraction. Now, if I do that, what I'm going to find is that if I combine the 8 through the 4 here and combine them with the 3 times 2 times 1, hey, I've seen that before. That's just 8 factorial. And then what I divided by down here, 3 times 2 times 1, that's just 3 factorial. And where did the 3 come from specifically? Well, that corresponds to all the blanks I didn't get to fill in. And that means that what the 3 means, it's 8 minus the blanks that I did fill in. It's the total number of blanks minus the blanks that I did get to fill in. And this gives us our expression for the total number of ways to make this 5-letter sequence. We're not going to evaluate this one because the number gets really big quite fast. So more generally, what's the principle we've kind of derived here for the k-permutation formula? So we often call this kind of task where I want to select k objects from a set of n distinct possibilities. That's the k-permutation task, and so the k-permutation formula tells me how many ways I can do it. So the k-permutation formula says that the number of ways to arrange k distinct objects from a set of n distinct possibilities is, and so we often have a notation for this. So we often call this P of n and k. So P of n and k just literally means the number of ways to arrange k distinct objects from a set of n possibilities. It's the number of k permutations on n objects. And the way we calculate P of n and k, it's n factorial divided by n minus k factorial. So it's the number of total possibilities factorial divided by the number that we're not choosing factorial. And if we wrote this out, it would be n times n minus 1 times n minus 2 all the way down to n minus k plus 1 all multiplied together. So with the k-permutation formula, we can answer any question we want of the form, how many ways are there to take k things from a set of n things and arrange them in some order?